Hello, welcome to another module in this massive open online course. So, we are looking at OFDM, an OFDM system and the specific application of linear algebra and the modeling and analysis of this system. So, let us continue our discussion. So, we are looking at OFDM, and where we had left in the last module is the following thing: considering an ISI channel with the channel taps H0, H1, Hn minus 1, where n equals the number of subcarriers, where n equals the number of subcarriers. What we had said is that these are the channel taps and the channel matrix. If you look at the OFDM system after the cyclic prefix and so on, the channel matrix can be has a very interesting structure. So, this will be H0, Hn minus 1, Hn minus 2, so on H1, and then H1 comes over here, H0 pushes to the right, Hn minus 1 also pushes to the right, you have H2, then H2 comes, rotates here, you have H0, you have H3, so on, and the last row will be Hn minus 1, Hn minus 2, so on until H0. And what we had said is, very interestingly, if you look at each row is obtained by circularly shifting the previous row. At the same time, each column is also obtained by circularly shifting the previous column, and therefore, is a very interesting matrix. Such a matrix is known as a circulant matrix, right? And this is the characteristic feature of OFDM, circulant. This is the circulant matrix with, if you look at the first column, if you specifically look at, this is the first column, the first column basically comprises of the channel taps. So, how to construct this matrix? Simply take the first column as the channel taps H0, H1 up to Hn minus 1, and then each subsequent column you shift it, downshift it by 1, and the one that pushes down you bring it back onto the top of the next column. So, the second column will be Hn minus 1, H0, H1 up to Hn minus 2, third column will be Hn minus 2, Hn minus 1, H0, so on up to Hn minus 3 and so on. And let us now look at interesting properties of this matrix. Now, what are the interesting properties? Now, the most interesting properties, now there are several, the most interesting property of this matrix is, in fact, the property of any circulant matrix, property of the matrix HC is that the eigenvector this is very interesting, the eigenvectors of HC are of the form that is, if you look at the kth eigenvector, I can write this as f bar k, which is 1 over n times 1 w raised to minus k, w raised to minus 2 k, w raised to minus n minus 1 k, right. This is the kth eigenvector, where you remember w equal to e raised to minus j 2 pi over n, all right, that is the definition of W. Let me just quickly check how we define W. W equal to, if you remember, W equal to, we have W equal to e raised to minus j 2 pi over n indeed. And now if you look at this quantity, this is nothing but, what is this f bar k? If you look at this f bar k is nothing but, if you observe this closely, this is the kth column of the IFFT matrix. This is the kth column of the IFFT matrix, and that is the interesting property of this. It is a very interesting property, and remember that is what we said. So, it is naturally, because it is circular, that it gives the impression that it is periodic. So, it has to have relation to sinusoids at complex exponentials. And what is that relation? The relation is essentially, if you look at this eigenvector f bar k, the eigenvector of this HC is essentially given by the kth column of the IFFT matrix. This is the interesting property. Let us prove this, right. So, let us try to see how this is. This is as follows, can be seen as follows. If you look at this, now first let us realize that the rth column, rth row, if you look at the rth row, that will be H r minus 0, H r minus 1, so on. H, I can, the only thing I need to do here is I can add a modulo n, right. So, this will be H r minus 0 modulo n, H r minus 1 modulo n, so on, and H r minus n minus 1 modulo n. So, this small n here, this indicates modulo n, right. And therefore, if you look at the rth row and if you look at the inner product with this, that is, let us consider the product HC times f bar k, and let us look at what happens to the rth row in this product. That is, the output is a vector, and we are asking the question, what is the rth element of that vector, and that will be 1 over n summation n equal to 0 to n minus 1 H r minus n modulo n W raised to minus n k. Okay. This is once again to remind you, this indicates that this is modulo which is equal to 1 over n summation n equal to 0 to n minus 1, or now substitute n equal to 0 to or now make r minus n equal to m, substitute r minus m equal to m. So, m also goes from 0 to n minus 1, this will become h m. There is no need for modulo n because m anyway goes to 0 to n minus 1. So, modulo m will simply be m because m is going from 0 to n minus 1. So, therefore, this will be h m w raised to the power minus n minus n k. So, this implies r minus n equal to m, this implies r minus m equal to n. So, this will be r minus of this is equal to 1 over n summation m equal to 0 to n minus 1 hm w raised to the power of minus, or in this case plus mk times this other quantity will be common, w raised to the power of minus rk. And now if you look at this quantity, this is interesting, this is summation, this is nothing but if substitute for w, this will be 1 over n summation m equal to 0 to n minus 1 h m e raised to the power of minus j 2 pi m k over n times w raised to the power of minus r k. And if you look at this quantity, this is nothing but the FFT or the DFT coefficient of the channel taps. This is nothing but the, in fact this is the kth DFT coefficient. In fact, this is the kth DFT coefficient of the channel tap. So, I can write this. So, this is essentially your h of k. So, this is basically your h of k times 1 over n w raised to the power of. So, if you look at h c times f bar k, and if you ask the question what is the rth element, that is what is the rth element of this, that is simply the hk, that is the kth DFT coefficient hk times 1 over n w raised to minus rk. This is the interesting aspect. So, hk, where hk, remember what is hk? Hk is the kth DFT coefficient, that is summation m equal to 0 to n minus 1 hm e raised to minus j 2 pi mk divided by n, right. That is if you take the channel taps and take the kth DFT coefficient, that is what it is. Now, write all this. So, therefore, if you write hc times f bar k, so therefore, write all the elements hc times f bar k equals hc, this will be hk, or this will be hk times 1 over n. What are the elements? 1, first element will be w, each element is w raised to minus r k. So, w raised to minus k, w raised to minus 2 k, so on w raised to minus n minus 1 k. And in fact, if you look at this now, interestingly, if you look at this, this is nothing but essentially the vector f bar of k. So, that is the interesting thing. So, essentially you have the relation hc of f bar k equals 1 over n or equals in fact hk times f bar k. So, this is of the form ax bar. If you look at this, this is similar to a x bar equal to lambda x bar, where x bar equals the, you know very well now, x bar equals eigenvector, lambda equals the eigenvalue. So, this implies that in this f bar k, this is the eigenvector of H c and the this DFT coefficient is the eigenvalue. So, that is the interesting aspect of this. So, the HKs, that is the DFT coefficient, the eigenvectors are the columns of the IFFT matrix and the eigenvalues are given by the FFT or the DFT of the channel tap. So, this is the interesting property of the circulant matrix. So, HC has the following very interesting property: HC eigenvectors equals columns of IFFT matrix and eigenvalues equals the DFT coefficient eigenvalues are the DFT coefficients of the channel taps. And this also implies that the eigenvalue matrix implies the eigenvalue matrix. If you look, eigenvalue matrix, this is equal to simply the column of the matrix which contains the IFFT columns of the IFFT matrix. So, this is simply the IFFT matrix, right. So, this is the eigen, I am sorry, this is the eigenvector matrix, right, and eigenvalue matrix lambda, the eigenvalue matrix is contains the DFT coefficients So, this is the eigenvalue matrix. This is the eigenvalue matrix. So, this is the eigenvalue matrix, basically contains the DFT coefficients. And we know what is eigenvalue decomposition. The eigenvalue decomposition of square matrix is nothing but the eigenvalue matrix, I am sorry, the eigenvector matrix times the diagonal matrix of eigenvalues times the inverse of the eigenvector matrix. Eigenvector matrix is the IFFT matrix, inverse of the eigenvector matrix is nothing but the inverse of the IFFT matrix, which is nothing but the FFT matrix, and that essentially completes this analysis, right. So, you have now very interestingly, if you look at it, HC any matrix, let me write the general property. This is can be written as the product of eigenvector matrix times diagonal matrix of eigenvalues times inverse of eigenvector matrix, which in this case implies HC equal to eigenvector matrix is the IFFT matrix F IFFT times the diagonal matrix of eigenvalues, which contains the DFT coefficients times F IFFT inverse, but F IFFT inverse equals FFFT. So, therefore, this is writing it explicitly F IFFT times your H0 up to Hn minus 1 times FFT HC, and this essentially, so if you look at this, this is the eigenvalue decomposition. Let me write this thing once again. H equal to F IFFT times H0 H1 up to Hn minus 1 times FFT, and this is essentially the what we call as the EVD. This is the eigenvalue decomposition of HC, which is now so for the circulant matrix. In fact, for any circulant matrix, the eigenvalue decomposition is given by the IFFT matrix times the diagonal matrix of eigenvalues, which are nothing but the DFT or FFT coefficients of the channel taps, followed by the FFT matrix, right. And in fact, let us also write the formula for the eigenvalue. You have lambda k equals h of k, which is basically summation m equal to 0, or you can write it as n equal to 0 to n minus 1 h of n e raised to minus j 2 pi k n by n. So, this is your kth eigenvalue, okay, and this is your matrix lambda, that is the diagonal matrix of eigenvalues. Okay. So, this is essentially the interesting aspect, or this is the most interesting property of the circulant matrix. And now what we are going to do is we are going to use this matrix in the OFDM system model, and we are going to simplify the OFDM system model and observe something very interesting, and that is what we are going to do in the next and the final module. All right. So, let us stop here and we will continue this discussion in the next module. Thank you very much.